The objective of this lecture is to provide the first part of the study of kinetics of a particle, and in particular, this lecture will focus on commonly used forces in dynamics. This lecture will be divided into the following parts. First, we will provide a definition of kinetics. In particular, kinetics of a particle, or also known as a point mass. Second, we will develop models for commonly used forces. And in particular, we are going to focus on the following types of forces, which will be contact forces, linear spring forces, and finally, gravitational forces. So kinetics. So kinetics is the study of the motion of systems, I should say the motion of physical systems, that arises due to actions applied to the system. Now, we're going to start this with particle kinetics, as we said. So particle kinetics is the study of motion of what are called point masses. Now, point masses, which are also equivalently particles, where a point mass is a zero-dimensional object in three-dimensional Euclidean space that has what's called inertia or mass. Now, when we use the term inertia or mass, we mean the same thing in this case because we're dealing with a particle. So a particle is one that has both inertia and mass. They're equivalent statements. So when we say inertia for a particle, that's the same thing as saying mass, and that's for a particle or point mass. Now, given the fact that we're dealing with actions, kinetics always starts with the concept of an action. So this is really important. So kinetics starts with an action applied to a system. If we have no action, then the system isn't going to be moved or isn't going to be set in motion due to some physical phenomenon that's actually occurring. So that's really important, that kinetics starts with an action. And for a particle, the fundamental action is that of what's called a force. So that's really important, that we're dealing with forces. So forces are the things that we have to start describing in order to be able to develop the laws that describe motion, which we'll eventually do. So a force is an action applied to a particle that causes the particle to move in some general sense. And the first thing we have to do is we have to develop models, or at least categorize different types of forces. So that's the first thing we're going to do here in this lecture, is we're going to develop commonly used forces in kinetics. Now this is for particle kinetics, but this also applies for kinetics of more complex structures, which include rigid bodies and fluids and other things, but we're dealing here with just particles. So these forces that we're going to be developing are ones that arise frequently, so we're going to use them over and over again. And they fall into the following categories. The first category is what are called contact forces. Now, a contact force is one that's due to the presence of another body that's in contact with a particle, and we'll develop models for that. The second type of force that we're going to be commonly using are what are called spring forces. And the third type of force that will come up frequently are what are called gravitational forces. And gravitational forces are due to attraction between masses, or between particles. So we're going to develop models for all of these. So the first thing that we want to do is we want to develop the concept of a contact force. So that's the first thing we're going to talk about. So we'll talk about contact forces. Now, what a contact force is when a particle is in contact with another body, that body imparts a force on the particle. Now, schematically, we're going to denote this body as a surface, which is going to be in the next picture. So schematically, this body is a surface, and we will describe what that surface looks like now. So here's what it looks like. So imagine that I have this object which is schematically going to be denoted as surface. Now this surface is in contact with a particle, P, which is of mass m. Now that particle, because it's in contact with the surface is going to impart a force, as I said. So S is equal to the surface with which the particle, which I'm going to denote P, of mass m, is in contact. Now, given that that's the case, I'm going to call F, and I'm going to call it FC, is going to be the force exerted by S on P. And that's also the contact force. Now, given that it's the contact force, we have to develop a model for this force. So now here's how this model is going to work. Is that the surface itself, I'm going to add to this diagram, has a vector which I'm going to call n. And n is the direction normal to the surface. So I'm going to say n is equal to the unit normal to S at P. So wherever the particle P is, there's a vector that's going to be normal. Now, when I say normal, what I mean is as follows, is that at this point P, there's a plane that's tangent to the surface. So I'm going to call this the tangent plane. So it's the tangent plane to the surface S at point P. So I'm going to say TPS is equal to the tangent plane to S at P. So what that means is, and what it implies, is that N lies orthogonal to the tangent plane. That's what I mean by this. Now, given that we have a tangent plane, we also can now define two vectors that lie in the plane itself. So if I'm looking down on this tangent plane, I have the normal, and then I can define two vectors that lie in that plane, which I'll do next. So this is a view looking what I'm going to call down on S at point P. So here's this tangent plane. This is that tangent plane that I drew in the previous diagram. So this is the tangent plane at point P to the surface S, and here's point P. Now, if I look out of the page, that direction is the direction N that I already defined. Now I'm going to define two other directions. It doesn't really matter what these two directions are, so I'm just going to put them in the in this plane, but they have to be orthogonal to one another. So I'm going to define these two directions as W1 and W2. Now W1 and W2, they lie in the tangent plane to S at P. And they have the following properties. That with the properties, that W1 dotted with W2 is 0, so they're orthogonal to each other. They're both unit vectors. And the third thing is that the basis, or this set, W1, W2, and N, is a basis for three-dimensional Euclidean space. So what that, of course, implies is that W1 crossed with W2 has to equal N. Now, given that I've defined this basis, W1, W2, N, I can now use this to develop the contact force. W1, W2, N can be used to model the contact force. And we do that as follows. So the contact force, Fc, is going to equal, it's going to have two parts. It's going to have an F sub F1 times W1 plus F sub F2 times W2 plus a third part, which I'm going to call N times N. And these these components that I've defined, because W1, W2, N is a basis, are such that I'm going to define F sub F to equal F sub F1 times W1 plus F sub F2 times W2. And this is defined as what's called the friction force. So the third component, which is N, which is equal to scalar N times little n, is what's going to be defined as the normal or reaction force. Now, because we're dealing with motion, we're going to make the following assumption. We're going to assume that P moves relative to the surface S. And furthermore, and this is also important, assume that S is a reference frame. So what we now have is we have a surface, which is a reference frame, and so therefore it's a collection of points whose distance from one another doesn't change, and it's a collection of at least 3 points, and it defines this thing called the surface. And so using that information, we can say let VPS equal the velocity of P as viewed by an observer fixed in S. And we're going to use this information to be able to develop the friction force. So we'll note that here, and then we'll come back to it in just a minute. The quantity VPS will enable developing the friction force, F sub F. So the next thing that we need to do is that we need to somehow figure out a way to be able to characterize this normal force, or this reaction force. So we're going to let something else. We're going to say let F be a function that describes the surface S. Now what that helps us with is as follows, is that using the fact that we now have this function F, we can use it to be able to define that vector N. So in particular, let F be a function of the position of P relative to an arbitrary frame. And I'll call that frame A. So we're going to add to this picture a little bit to be able to figure out how all this works. So now I have an arbitrary frame A. Here's my frame A. And I'm going to put a point O. And as has been the case with kinematics, O is fixed in A. And here I have this surface, which is the same surface that I had before. So I've just added to this picture. I have this point P, which is of mass M, and I have the normal vector, which was the same thing that I had before, but I'm not going to draw the normal this time. I don't really need it, which is that I'm going to take the vector that connects O to P. So I'm going to say let R equal the position of P relative to O. Remember, O is fixed in S. And given that F is going to be a function of R is equal to the function that describes S. So basically, this function, and this function in particular, is going to be such that F of R is equal to 0. This is the function that describes S. Now, this is common in analytic geometry, that we define functions as level sets, and we say that that level set in this case is equal to 0. This function is this locus of points that defines this surface S. And now, given that, the gradient of this function, that we know that the gradient of F with respect to R is orthogonal to S. So that implies that the normal vector lies in the direction of the gradient of F. So now we can use this to be able to define that direction that's normal. So we say let the gradient, we're going to use a nabla symbol, R of F of R equal the gradient of F with respect to R. So this may not be a unit vector, but we know n is a unit vector. So n has to equal the gradient with respect to R of Fr, which is equal divided by the magnitude of the gradient of R of Fr. Now, in order to be able to sort of quantify what that gradient is, the gradient of R of Fr is the same thing as saying the partial of F with respect to R. They're exactly the same thing. So now we have two things. These are the two quantities that are going to help us be able to figure out this contact force. So we then have this velocity of point P is viewed by an observer fixed in S, and n, which depends upon this quantity, the gradient with respect to R of Fr. And we can use these two things together to be able to figure out the contact force. So here's how it works, is that we're going to start with the friction force, and we're going to work our way forward from there, which is there are two types of friction. So two common types of friction. And they are what are called Coulomb friction and second, what's called viscous friction. Now, these models are different, so we're going to develop each model. So we're going to develop a model for both Coulomb and viscous friction. So we'll start with Coulomb friction. So for either friction model, we're going to make the following assumption. We're going to assume that the velocity of P relative to S is not equal to 0. This assumption is equivalent to saying that P slides on S. Now, using that assumption, we're going to develop Coulomb friction and viscous friction, which we'll get to in just a minute. So Coulomb friction has the following model, which is that the force is equal to minus a constant of proportionality called mu times the magnitude of the normal times VPS divided by its magnitude. So that's like a unit vector when I take VPS and I divide it by its magnitude. Mu is what's called the coefficient of dynamic Coulomb friction. And the reason it's called dynamic Coulomb friction is because the velocity of P relative to S is not equal to 0, which means P is sliding on S. So it's also called the coefficient of sliding friction. Now, that's the first model. That model is proportional to the normal force. So you'll notice that Coulomb friction depends upon the magnitude of N. The second model for friction is what's called viscous friction. Now, viscous friction has a very different model from Coulomb friction, which is that viscous friction has the model that F sub F is equal to minus C times the velocity of P relative to S. It's actually linear in this velocity of P relative to S. And C is what's called the coefficient of viscous friction. So those are the two models for friction that commonly arises in dynamics problems. So we've got Coulomb friction and we've got viscous friction. Now, there's one particular case of both friction models that's important, which is that up till now we've been dealing with a surface. And this case is for a particle sliding on a curve instead of a surface. So this is the case where this is contact forces for a particle sliding on a rigid curve. Now, the reason that this has to be dealt with separately is because a surface is a two-dimensional object. So S was a two-dimensional object. In three-dimensional Euclidean space. But a curve, which we will denote C, is a one-dimensional object. So as such, we actually have to deal with it a little differently. So here's what the diagram looks like with a curve. Is that here's my curve, and it's a rigid curve, so it defines a reference frame. And there's a point on this curve, which is my particle, P of mass m. Now you remember that, so there's P, it has mass m. Now you remember that for a curve, kinematically, we can actually define the velocity of the particle as viewed by an observer fixed to the curve. And that direction actually lies along the tangent vector to the curve. So we're actually going to use an intrinsic basis in order to be able to do this. And then we have the principal unit normal to the curve. And finally, we have the principal unit binormal to the curve. So ET, EN, and EB is an intrinsic basis relative to the curve C. So now what we can do is we can actually define the forces F sub F and the normal force, which is that we know again that the contact force is equal to the friction force plus the normal force. In this particular case, though, the friction force lies along the tangent vector. It has to, because it's tangent to the curve. Just like the two vectors W1 and W2 lied in the plane that was the tangent plane to the surface, this tangent vector lies along the curve. So that means that when we do the friction force, either Coulomb friction or viscous friction, we wind up getting the following results. So for motion along a curve, we actually wind up with almost exactly the same form of the results for Coulomb friction and viscous friction. For Coulomb friction, the force is minus mu times the magnitude of the normal times the velocity of P as viewed by an observer fixed in C divided by the magnitude of the velocity of P as viewed by an observer fixed in C, which is the curve. And viscous friction looks very similar to what it looked like before, except for now we're dealing with the curve, which is that F sub F is equal to minus C times VP C. So that's actually not any different really from what we had before, but the normal force changes, and this is what's important. So again, for motion along a curve, this is all for motion along a curve, is that in the case of a curve, the normal force lies in the directions EN and EB. What that means is that the normal force has two components, N sub N EN plus N sub B EB. So then in the case of Coulomb friction, that would imply that the magnitude of the normal force, which is used in the Coulomb friction model, is equal to the square root of N sub N squared plus N sub B squared. So it's important to understand that in the case of a curve, the friction models look very similar. We're just dealing with a curve instead of a surface, but the model for the normal force changes because we have two components of normal force rather than having one component of normal force. So you have to keep these two things straight. If you're dealing with a surface, you have to do it the way I described it before. If you're dealing with a curve, you have to do it in the way I described for a curve. And that takes us to the end of the discussion for contact forces. And the next thing we're going to do is we're going to do spring forces. So now let's describe linear spring forces. So first, let's provide a schematic of a linear spring. So suppose I have an arbitrary reference frame A, and I have a point O, and O is fixed in A. Now, the linear spring is shown schematically as follows. First, I have a point which is at one end of the spring. I'm going to call this point Q. And then I have the spring itself. So here's the spring. And then at the other end of the spring is the particle. That's the particle that has mass m. And this point Q is what's known as the attachment point of the spring. And then here's the actual spring itself. Now, the linear spring exerts a force on P. And we're going to model this force. I'm going to do it as follows. Is that first, we're going to use the length of the spring to define the size of that force. So we're going to say let L be the length of the spring. And let L0 be what's called the unstretched which is equivalent to the uncompressed length of the spring. What that means is that when the spring has a length L0, there's no force that's being applied by the spring. It's only when the spring has a length that's not equal to L0 that there's a force applied. Now, we have the following assumptions about this linear spring in terms of the way the force is exerted. So for a linear spring, the following is true. Let's say the following are true. First is that the force is proportional to the stretched or compressed length of the spring. The second is that the constant of proportionality is denoted K. And that's what's called the spring constant. So K is called the spring constant. And third is that the force lies in the direction opposite the stretch or compression. And what that means is that if the spring is stretched, the force lies in the direction opposite the fact that the length of the spring is longer than the unstretched length. If the spring is compressed, it again lies in the direction opposite the fact that the spring is now shorter in length than the unstretched or uncompressed length. So we're going to use all these properties to be able to model the spring. So there are two different cases that we have to consider. So the two cases are, one is L minus L0 is bigger than 0. That's the case of stretch. And the second one is L minus L0 is less than 0, and that's the case of compression. Now, in both cases, so in either case, the force is proportional to the product of K and L minus L0. And that's because I set up above that the force is proportional to the stretched or compressed length of the spring, and L minus L0 is the stretched or compressed length of the spring, and then the constant of proportionality is denoted K. Now, it's important that the other thing that, just for complete clarity, it's actually the absolute value of L minus L0 that matters, because if L minus L0 is bigger than 0, then that's a positive number. But if L minus L0 is less than 0, that's of course a negative number. And the length of the spring is actually the absolute value of L minus L0. So we'll work through that when we deal with both of these cases, as we'll do now. So in order to deal with both of these cases, I'm going to say let US equal the position of P relative to Q, all divided by the magnitude of the position of P relative to Q. What that is if I draw my spring again, and here's point Q, which is the attachment point, and here's point P, the vector US lies along the direction from Q to P. So US is the unit vector along QP. So now let's consider both cases using the information that we just developed, which is case 1 is L minus L0 is greater than 0. This is the case of stretch. In the case of stretch, we know that the spring force is proportional to K times L minus L0. Now what we have to do is we have to get the direction of the force correct. Well, US is the unit vector in the direction from the attachment point to the particle, but you can see that because L minus L naught is bigger than 0, this force is in the wrong direction, because this force has to be in the direction from P to Q, not in the direction from Q to P. So there has to be a negative sign in front. And that's the model for the case of stretch. But if I put this now in terms of this position of P relative to Q, I get minus K times L minus L naught times the position of P relative to Q divided by the magnitude of the position of P relative to Q. Now, of course, to be complete about this, we actually can write this purely in terms of the position of P relative to Q, because L itself is equal to the magnitude of the position of P relative to Q. That's the length of the spring. Minus L naught times the position of P relative to Q, all divided by the magnitude of the position of P relative to Q. So that's the model for the case of stretch. Now let's do the case of compression. So this is case 2. This is L minus L naught is less than 0. And as I said, this is compression. Now in the case of compression, we once again have that the force exerted by the spring is K times L minus L naught. But notice in this case that L minus L naught is negative. So if I put US here, look at the direction that the spring force is pointed. It's actually pointed along the direction from P to Q, because L minus L naught is a negative number. So it's in the wrong direction again, which means you have to have a negative sign in front, because that rectifies the direction and makes it such that it's along the direction from Q to P. So once again, if we go through the process, we get minus K times L minus L naught, and then we get the position of P relative to Q, all divided by the magnitude of the position of P relative to Q. And if I make a complete substitution, then once again, F sub S is equal to minus K times the magnitude of the position of P relative to Q minus L naught times the position of P relative to Q, all divided by the magnitude of the position of P relative to Q. So in both cases, the spring force is the same. So we'll write down the model for one model that has been developed for both cases. It's applicable in both cases. So therefore, the force exerted in a linear spring is equal to minus k times the magnitude of the relative position between the attachment point and the particle minus the unstretched length times the unit vector from the attachment point to the particle. That is the model for a linear spring force. And you'll notice that it's the same in both cases. So let's just reiterate what these quantities are, just to be complete about this, which is that the magnitude of the position of P relative to Q is equal to L, which is equal to the length of the spring. L naught is equal to the unstretched equivalently uncompressed length of the spring, and then K is the spring constant. And that completes the model for the force exerted by a linear spring on a particle. So the last type of force that will be studied in this lecture is gravitational force. We'll talk about gravitational forces. Gravitational forces are also what are called mass attraction forces. So in order to be able to see this, let's suppose we have two particles. So let Q and P be particles of masses m sub q and m sub p, respectively. Now here are these two particles. Here's Q and here's P. And there's a vector that goes from Q to P, which is the position of P relative to Q. This particle has mass m sub q, and this particle has mass m sub p. Now, the gravitational force is defined as follows. So what we're going to do is we're going to say let, I'm going to call it R, equal the magnitude of the position of P relative to Q, and that's the distance between Q and P. Now the gravitational force has the following form. It's proportional to the inverse of the square of the distance, and it's defined in such a way that the force exerted on any particle, whether it be Q or P in this case, is in the direction from the other particle to the particle on which the force is being exerted. So let's write that down, which is that it's proportional to the inverse of the square of the distance between the particles, and it lies in the direction from the particle on which the force is being exerted to the particle exerting the force. Now what that means is that we'll put this on another page just to be a little bit clearer with the direction of the force. So once again, here are the two particles. There's Q and there's P. So given what I just wrote, the force exerted by Q on P lies in the direction from P to Q. So this is the force exerted by particle Q on particle P. The force exerted by particle P on particle Q, which lies in the opposite direction. And we have the following, that the force exerted by particle Q on particle P is negative the force exerted by particle P on particle Q. So we just have to do one of these and we get the other one automatically. So we know that the force exerted by particle Q on particle P, so this is what this is defined as. This is the force exerted by Q on P. And this force is proportional to the inverse of the square of the distance, and it lies in the direction from P to Q. So I know that it has to be proportional to something over r squared, and it's proportional to the square of the distance times some constant of proportionality, and it has to lie in the direction from P to Q. So this has got to be the position of P relative to Q divided by its magnitude, and then because it's in the direction from P to Q, it's got to be negative. So that's what this force has to look like. So now of course, the position of P relative to Q in magnitude is just again equal to R. So this is minus C over R cubed times the position of P relative to Q. Now we have to figure out what C is. So let's determine C. Well, it turns out that C is a constant that is proportional to the product of the two masses, and it's also proportional to a constant called G, which is Newton's universal constant of gravitation. And we'll put that on the next page. So C is a constant that depends on the product of the two masses and a constant called G. Now G is what's called Newton's universal constant of gravitation. So because of the dependence here, we see that C is equal to G times the mass of P times the mass of Q, which then implies that the force of gravitation, which is the force exerted by Q on P, is equal to minus G times the mass of P times the mass of Q, all divided by R cubed, times the position of P relative to Q. And we're going to replace this. So we're going to say, let Fg equal Fqp be the gravitational force exerted by Q on P, which implies that the gravitational force is equal to minus G times the mass of P times the mass of Q over R cubed times the position of P relative to Q. And of course, that is equal to minus the force exerted by P on Q. So we automatically have the opposite force because these forces are equal and opposite one another. So So that takes care of gravitational force and how it's actually defined, and quantitatively how it's described. So now we have the model for gravitational force. Now, before we leave this topic of gravitational forces, let's discuss one other concept, which is what's called the force of gravity. Now, gravity, as I've stated here, is nothing more than an approximation of the force of gravitation. So this is an approximation of a gravitational force in the case where a particle lies in close proximity to the surface of a large sphere of mass big M. So here's what the picture looks like. I have a sphere. It's a large sphere, and it has mass big M, and it has a radius, which I'm going to call big R. So here's the center of the sphere at point O, and the radius of the sphere is big R. Now we're going to make an assumption here. We're going to assume that all mass of the sphere is concentrated at O, which is the center of the sphere. Now here's the particle. The particle is up here, and it's in close proximity to the surface of the sphere. So the position of P relative to O is as I've drawn with that vector, but there's a point Q on the surface of the sphere. Now Q lies on the surface of the sphere in such a way that the distance from Q to P, so the magnitude of the position of P relative to Q, is going to be denoted H. And we're going to assume that H is much, much less than R. And we're also going to assume that M, which is the mass of the sphere, is much, much bigger than the mass of the particle. This is the particle that has mass little m. So now let's look at the force of gravitation in this particular case. So we know the following. So using the force of gravitation as previously derived, we have that the force of gravitation, which in this case is equal to the force exerted by the sphere on P, is equal to minus G times the mass of the particle times the mass of the sphere, all divided by R cubed times the position of P relative to O. And I have to be clear here, where R is equal to the magnitude of the position of P relative to O. Now I can write this in a slightly different form, which is that I can equivalently say that the force of gravitation is equal to minus G M times big M all divided by R squared times the position of P relative to O all divided by R. And in order to make this a little bit easier to deal with, we're going to say let U equal the position of P relative to O all divided by r, from which we actually get that the force of gravitation is then equal to minus g little m big M all divided by r squared times u. Now u has a special term. It's actually what's called the unit vertical direction. So it's the unit vector in the vertically upward direction. That's what we actually call vertically upward. It's orthogonal to the sphere. So in order to see this, let's draw this picture a little bit differently from the way we drew it before. So here's the sphere again, and this point Q, which is on the surface of the sphere, is such that there's a tangent plane to the sphere at this point Q. P is up here. The vector from Q to P lies normal to the tangent plane, because if I take this all the way back to the center of the sphere, which is here at point O, then this plane that I've drawn, this is the tangent plane to the sphere at point Q. So if I look at this in this perspective here, here's my tangent plane. Here's point Q. P is up above the point Q, and that vector from Q to P, this position of P relative to Q, is orthogonal to the tangent plane at point Q. So now that's the picture. So now let's go back to our model. So returning to the model, the force of gravitation is equal to minus g little m big M over r squared times u. But r is equal to the magnitude of the position of P relative to O, which is equal to capital R plus h, because h is the height above the sphere. So we know that h is much, much less than r, or equivalently r is much, much bigger than h. So that implies that r can be written like this. We can say that r is, if I factor out the big R, I get 1 plus h over r. But because h is much, much less than r, that implies that h over r is much, much less than 1, which implies that r is equal to r times 1 plus h over r is approximately just r. So therefore, the force of gravitation is approximately minus g m m all divided by big R squared times u. And what I'm going to do is I'm going to break this up into the following pieces. I'm going to put the m in front, and I'm going to put a minus sign there, and I'm going to put g times m all divided by r squared. I'll put that in brackets times u. Now this constant g times m over r squared is the interesting part. That quantity is actually what's called little g, and it's the local acceleration due to gravity. So this becomes minus mg times u. So note that this is an approximation, and the approximation now works as follows. So we then have g is equal to g times big M all divided by r squared. And this is what's called the local acceleration due to gravity. And it's an approximation that applies when you have a particle in close proximity to a large body. In this case, it's a sphere. So that winds up giving you the force of gravity is equal to minus mg times u, where recall that u is the local vertical upward. Now, this is an approximation. It's really important. This is not the force of gravitation. It's an approximation to the force of gravitation when a particle of mass little m lies in close proximity to a sphere of mass m much, much bigger than m, and the distance from the particle to the sphere is much smaller than the radius of the sphere. So in other words, what this is saying is that m is much, much bigger than little m, and r is much, much bigger than h, where we recall that h is equal to the magnitude of the vector from q to p, where q is on the surface of the sphere, and r is the radius of the sphere. So this is what's called the force of gravity. So that takes us to the end of this lecture. And to provide a summary, what we did in this lecture was we first defined kinetics for a particle, and then we developed models for commonly used forces. And in particular, we first studied contact forces. We then studied spring forces. And finally, we studied gravitational forces. Using these force models in the next lectures, we're going to work with Newton's laws. We're going to define Newton's laws of motion, and then we're going to study examples where we actually use these different types of forces in solving problems in kinetics of particles.